good morning, Simon's Institute. Today we have a third day of the workshop, and it's devoted to streaming. And there's nobody better to introduce streaming than very experienced streamer, Andrew McGregor from University of Massachusetts, who will tell us about the last 20 years of graph streaming. And in the spirit of the workshop, he's going to compress all of it in slightly over 1 hour. All right, go ahead.
Streaming in real time.
Yeah, real time.
Okay, so we've heard a lot about graph algorithms in the last 2-3 days. This is all motivated by the fact that there are various big graphs out there that we need to process. So the classic examples people often mention are things like social networks, the web graph, call graphs, protein interaction networks, the interaction between neurons in the brain. And just graphs crop up, you know all this. Graphs crop up all over the place. Just whenever you have information about basic entities and the relationship between these entities, there's a graph. The challenge is that all those classic algorithms that you learned in grad school or undergraduate don't really work very well on these massive graphs, and this is for a variety of reasons. Often the graphs are too big to be stored in memory. Sometimes they're stored across multiple machines. Sometimes the underlying graph is kind of updating over time. And so what I've been doing, and what many people in this room has been doing, really is trying to kind of invent the new textbook algorithms for these modern massive graphs. Okay, the particular focus of this talk and my research is on streaming algorithms. So in the context of graphs, there's two main variants I want to think about. One is the insert-only model. So you have an input stream that just consists of the edges of a graph ordered arbitrarily. And this all kind of builds up a graph. At the end, there's been a graph defined, and you're interested in properties of that graph. A slightly more complicated variant of this model is when the stream consists of edges being both inserted and deleted from the underlying graph. And so the goal is you want to understand properties of this graph. Like maybe you want to work out whether the graph is connected, what's the size of the maximum matching, et cetera, et cetera. The catch is you typically only get one pass over the stream, and you're only allowed a small amount of memory. So this is just the classic kind of data stream applied to graph problems. Before there was work, so there's been about 20 years of work on graph streams. And before that, there was like a lot of work on numerical streams. So the stream would consist of a sequence of, say, integers, and you're trying to work out kind of quantiles of the underlying distribution or heavy hitters, things like that. And there's now a growing body of work on problems with more structure, things like distances and cuts and eigenvalues and random walks of graphs being defined in the data stream model. So I will not be able to cover 20 years of material in 70 minutes. But fortunately, there's a couple of great surveys there's one OK survey that I wrote, and there's one great survey Sefia wrote, more focused on the lower bounds that you can access. Sefia and I have also taught courses on graph streaming at our respective institutions, and all the slides are available. I should say a lot of this stuff is really nice to teach. So even if you just want to incorporate into a general graduate algorithms class, it's just fun, surprising stuff. Okay, so that's streaming. I should say, any questions? Feel free to interrupt me at any time, of course. So going hand in hand with streaming, we have linear sketches. It used to be I could say sketches and everyone would understand I meant linear sketches, but that's no longer the way of the world. So the idea behind linear sketches is you have your input, which is encoded as a big long vector. Maybe every coordinate, maybe this is a binary vector, and every bit corresponds to the presence or absence of an edge in the graph. And rather than process this original vector, in various situations, what we do is we first of all take a random matrix and project this big long vector that contains all our input information down to a short projection. And to work out information about our original vector, we instead look at the projection of the vector. And if we've chosen our random matrix M from the right distribution, hopefully the projection contains enough information to answer whatever question we're trying to ask about V. Sometimes M is a very simple random matrix. Sometimes every entry is like a +1 or -1 with equal probability, and there's no structure. Sometimes M is a very complicated, random, structured matrix, depending on the application. Okay, so sketches have been around for a while. A lot of the initial results were for relevant to numerical statistics. Things like Johnson-Lindenstrass are examples, where you're estimating the distance between vectors based on their projections. More generally, there's a kind of extensive kind of theory of these things connected to things like hashing, compressed sensing, metric embedding. The idea of randomly projecting data kind of just crops up in a variety of models, a variety of kind of computational models, for two main reasons. One, it's embarrassingly parallelizable. So if you've got some data of some vector x, and I've got some vector y, and really what I want to do is I want to compute the projection of x plus y, well, you guys can go away and work out m times x. I can work out m times y. We can just add up the projections and we've got a projection of the added vectors, because that's how matrices work. It's also applicable to stream processing. The idea being that maybe the stream is encoding updates to this underlying vector v. And so if you've computed m times v so far, and then the next stream element says the ith coordinate of v is incremented by 1, well, how do you update the projection m times v? Well, you just take m times v plus 1 copy of the ith column of m would be exactly the same as m times v with that update. Okay, so the goal of my talk, as I said, there's been a lot of work done on graph stream algorithms. My goal is to do a couple of different things. Like, I want to kind of highlight some results which, in my opinion, are particularly surprising or particularly elegant or particularly fun, and often illustrate important techniques. The other thing that I realized as I was preparing this talk was that a lot of the algorithms that out there are what's called semi-streaming algorithms. Okay, so all that semi-streaming algorithms means is that I said that as you go through this stream to process these edges, I said you had limited space. Now, if you had space, if you had n squared space, you could store all the potential edges in the graph. So the semi-streaming model is just saying that you're allowed exactly, or O tilde n space, where n is the number of nodes. So it's a little bit of a strange term, kind of semi-streaming, because semi-streaming is just a specific case of streaming. There's nothing non-streaming about semi-streaming. It's also maybe a little strange to mention a specific space constraint to give it a name. But it turns out that many problems are infeasible with less than n space, and a little bit of magic kind of happens around the kind of O tilde n space. So as I was preparing this talk, I realized that kind of this paper that first of all looked at the semi-streaming model is 20 years old this summer, which is a sobering thought. So this was work by Joan Feigenbaum, Sampath is over there, and myself, Sid Suri, and Jian Zhang. So at various points in this talk, I want to say, what did we do 20 years ago? I kind of, what open questions did we leave? What homework did we give the community? And I want to grade the community and how well they did in answering those open questions. Okay, so that's my other agenda in this talk. The overall narrative of the talk, I first of all want to introduce an important primitive that crops up a lot in the context of graph processing, which is L0 sampling. I'll give a couple of brief applications of that. The tagline, if you like, of this section is that one thing you can do when you process massive data streams is you can uniformly sample the edges. Okay? It's not trivial how you can do that, but you can do that. And for some problems you might want to solve, that is all you need to do. We'll then move on to looking at graph matchings, and we'll see how you can use sketches to compute exact matchings, approximate matchings, and matchings of planar graphs. The tagline of this section will be that sketches enable interesting types of non-uniform sampling that are useful for graph problems. I'll then move on to a third section on connectivity, where I'll show how you can use sketches to analyze edge and node connectivity, build cut and spectral sparsifiers The tagline here will be something called homomorphic compression, which sounds fancy, but I'll get into what it is. It's not that fancy. Where the idea is that you sketch the data first, and then you compute with the sketches afterwards. If I have time, I'll then talk about some other fun uses of randomness in the context of graph streaming related to problems like independent set, kind of coloring, correlation clustering. Okay. Any questions? Okay. So this L0 sampling technique crops up all over the place. Basically, what it allows you to do in the context of graph streaming is that you have sequences of edges being inserted and deleted. And an L0 sampling algorithm is an algorithm it's going to use there are L0 sampling algorithms using a tiny amount of space, polylogarithmic space, that return a random sample amongst the edges that have been inserted and not deleted. Okay. Notice if there's no deletions, this would be a pretty trivial task. Like if there were just kind of a sequence of m edges being inserted into a graph, ahead of time, you could just pick a random number between 1 and m, go through the stream, and when that edge arrived, pick it up. There you go, there's a random sample. It's not clear how you do that if there are edges being inserted and deleted. Okay. Most of the time, we'll be able to use L0 sampling as a black box, but it will be important that it's enabled by using one of those random projections, one of those linear sketches. I'll go into this black box a little bit briefly, just to not leave it as a mysterious object in a second. But before I do, I just want to mention some brief some sample applications, excuse the pun, in graph streams. It wasn't a deliberate pun, but some sample applications in graph streams. One of which is that if you want to, if you're interested in estimating the density of the densest subgraph in a graph, one thing you can do is you can just sample n divided by epsilon edges uniformly at random, look at your graph of those sampled edges, compute the densest subgraph in that sampled graph, and you can work back to getting a 1 plus epsilon approximation to the density of the densest subgraph in the initial graph. Another application is that if you sample n over epsilon edges from a graph, and then compute a vertex cover of just those sampled edges, then that vertex cover will cover all but an epsilon fraction of edges in the initial graph. Awesome, huh? Okay. Well, this seems like well motivated. This seems less so. Why should you care about this result? Hold that thought, and we'll come back to it. So as I said, just like so we'll use L0 sampling as a black box, so a polylog n space algorithm that allows us to sample edges uniformly. Let me just briefly go into what the sketch would look like that would enable something like that. So L0 sampling, so it's enabled by a sketch. So there's a random matrix M that's projected down from long vectors down to short vectors, such that for any long vector, we can find a random non-zero entry of the vector from the projection with high probability. So the random matrix is going to look like this. So in the first row, there's going to be all ones. And next row, every entry is going to be 1 probability half. Next row, every entry is going to be 1 probability quarter, an eighth, etc. So there's going to be most log n rows of this thing. And then if you apply this random projection to an arbitrary vector, this is my arbitrary vector of today, then what happens? Well, if I look at the projection, a whole bunch of stuff collides in the first entry. Some stuff collide in the second entry. Towards the bottom entries, I pick up no entries from my arbitrary vector, but at some middle points, I isolate a single entry. And that single entry is going to be uniformly distributed amongst the entries of X. Okay. That's the basic idea. Now, obviously, there's some details. Like, if you're just doing this projection, how do you know when if you're just looking at this thing, how do you know when an entry corresponds just to a single entry of A? Well, you can fix that up. This is actually just finding a value of the vector A. But if you want to find the corresponding index, again, you can fix that up. But this is just the general idea behind L0 sampling. I didn't want to leave it too much as a black box. Okay, any questions? Yeah.
Space, but storing that matrix is already
fantastic question. So all these these things are typically not fully random matrices. These are defined by hash functions. So you'll have a hash function for each row, which is going to give you the values, these zeros and ones. You don't, fortunately, you do not need to store this matrix explicitly. This is all enabled by hash functions. Thanks very much for the question. I'm sure many people were thinking that. Okay, let's go into matchings. So uniform sampling we can do efficiently. It's great for some problems. Is it great for matching? Fortunately not. So if you imagine a graph like this, where we have kind of n over 4 isolated edges, and a clique on n to the 0.9 nodes, and we start uniformly sampling edges, then almost all the edges that we sample are going to come from the clique. The biggest matching in the clique is of size order n to the 0.9, whereas there's all these, like, there's n over 2 isolated edges there. So if you're trying to find edges in a large matching, you want to be picking up these edges, not these edges. So uniform sampling isn't what you want. So we need different forms of sampling that are A, useful for graph problems, and also B, that we can actually hope to implement in graph streams. Okay. But let's wait on sampling for a second and go back 20 years. Okay. So 20 years ago, with that paper with Sampath, what did we know how to do at that point? Well, we had one very simple observation. So if you have just edges being inserted, and you're allowed order n-ish space, then one way to compute a matching is that you pick the first edge, and you keep on going. Every edge that comes in, you add it to your collection if it doesn't share an endpoint with an edge you've already stored. Okay, so you're just building up a greedy or a maximal matching. And it's not hard to show that a maximal matching is a 2 approximation. So just with edge inserts and semi-streaming space and one pass, if there's no deletions, you can get a 2 approximation. Okay, pretty easy. Slightly more complicated is if these edges have weights, but we came up with a little variant of that sort of kind of greedy approach when there's weights. And intuitively, basically at every point in time, we're maintaining a matching. A new edge comes in. If it doesn't have shared endpoint with anything we're currently storing, we just add that edge to our collection. If it does, we look at the weight of this new edge versus the weight of the edges that it shares an endpoint with that we're currently storing. If this new edge is much heavier, much better than the stuff it conflicts with, we throw out the stuff it conflicts with and add the new edge. If not, we just ignore this new edge. Okay? So that was the gist of this weighted matching algorithm. So you see the edges one by one. If the weight of the new edge is some factor alpha bigger than the edges in M that share an endpoint with E, we'll add E to our collection throughout the conflicting edges. Now, how should alpha be set? We don't want alpha to be too large because then there may be kind of good edges that come in that we end up ignoring. But we also don't want alpha to be too small. Like if we set something kind of alpha to be something like kind of 1 plus epsilon, what could happen? Well, we see an edge like this of weight 1. Then we see an edge slightly better adjacent to it, of weight 1.1. Then another edge, weight 1.2. Then an edge of 1.3, 1.4. If alpha was set close to 1, we're going to see this path of edges, and we're going to end up only picking the last edge because we were very fickle. Every new edge came in was slightly better than the edge we had, so we changed. Okay, so we'll end up with one edge, whereas we could have ended up with roughly n over 2 edges. Okay. So you don't want alpha to be too small, but like in our paper, we said alpha to be 2, and we got our 2 approximation. Okay, experience has taught me not to go through charging arguments in public, so I will not go through the analysis of the approximation factor and the charging argument. But when you set alpha equals 2, you get the 6th approximation. Okay, so has there been any progress in the last 20 years? How have you guys done? Well, that silly, greedy maximal matching algorithm, we haven't beaten it. 20 years of trying, we haven't beaten it. Like, the best you can do in semi-streaming space in one pass is still a factor 2. There was a breakthrough result by Sepia like 1 year ago that says that if you increase the space from n to n squared divided by 2 to the power log star n, you can beat it. but you can't beat it like anything less than that so far. This is a central open problem. We have another couple months of the program. Please solve. Okay. For weighted, however, we have made a bit of progress. And Sesh and Slobodan both had like slides in their talks where they got to show like real data that would appeal to practitioners. This is what I'm going to do for weighted matching. So this is my graph of approximation ratios over time. Okay. So back 20 years ago, we had a factor 6. And then over time, people have subsequently improved it. And so we can now pretty much approximate weighted matchings as well as we can approximate unweighted matchings, essentially up to a factor 2 or 2 plus epsilon. So let me briefly go through this last result from, I guess, SOTA 2017. I think it won the best paper. Although some of the analysis I'm going to use is by Moshin and David Weitz that came along subsequently. So the algorithm has that similar sort of flavor, like you process each edge, like one at a time. If the weight of that new edge exceeds some threshold by some factor 1 plus epsilon, you store it, and if not, you ignore it. So in particular, what the algorithm is going to do is it's going to, it's a semi-streaming algorithm, so it's allowed to maintain some information per node of the graph. So we're going to maintain a value yv for every node v. Initially, those values are 0. Okay. And as those edges come in, we compare the weight of the edge to the sum of the values on the endpoints. Okay. And if it's bigger than the sum of the values by like a factor close to 1 or 1 plus epsilon, then we're going to store E, and we're going to increment the values at U and V. Okay. So you end up having this rule for storing a bunch of edges. So some set of edges are stored. Don't know how many yet. And then in post-processing, it suffices just to compute the best matching amongst the stored edges. Okay. So let me give a brief idea about how this algorithm, why this algorithm has the properties it does. So it's certainly one pass. How much space does it use? Well, if you think about it, for every node V, YV, you can argue every time you store an edge incident to V, YV is going to increase by a factor of 1 plus epsilon. I won't go through it, but this is just a function of plugging in the fact that W is bigger than this, and that you're going to increment WV by this amount. Push that together, you get a 1 plus epsilon increase. So every time you store an edge incident to V, YV increases by a factor 1 plus epsilon. And so if all the edge weights are between 1 and W max, you can argue that at most log base 1 plus epsilon W max edges will ever need to be stored on a single node. And so this applies to all nodes. So we end up having n times log base 1 plus epsilon times W max edges stored in total. Where does the approximation ratio of 2 plus epsilon come from? I'm not going to be able to prove this fully, but let me give you some intuition. Now, there's the intuition in Moshin and David Weitz's paper expresses this in terms of fairly naturally in terms of linear programming. You can actually do this without linear programming, without going into too much of a detailed charging argument, as follows. So basically, if you follow through this logic, what you'll notice is that after an edge E appears, if E has endpoints U and V, the value of YU and YV will be at least W. Okay? So this applies to every single edge, in particular, every single edge of the maximum weighted matching. So from that, you can argue that the weight of the optimum matching, the optimum weighted matching, is at most a 1 plus epsilon factor larger than the sum of these Y values. The other side is a little tricky, so I'll leave it as an exercise. But it's a feasible exercise to do. If you think about it, every time you increased one of these YU or YV values, you stored the edge that came in that was responsible for pushing that YU or YV value up. Okay. So using that, you can argue, after sufficient coffee, that there exists an M amongst the stored edges such that the weight of the matching is at least half the sum of the Y values. And so combining this statement and this statement, I guess I have a pointer that sees me walking, you get your half approximation. Okay, so weight and matching, we had some success. Okay. At which point you're thinking, yeah, but that unweighted problem, that's still kind of annoying. Can we really not do any better than a factor 2 approximation, even for the unweighted case? Well, yes, if you take multiple passes. Now, most of the streaming model is focused on single pass, but there's now a kind of a rich, kind of a growing body of work where you're allowed to take maybe a small number of passes. Like ideally constant, but for various problems, log or log is still very interesting. Okay, and that's the case for matchings. If I allow you 1 over epsilon log n passes or log m passes, you can find a 1 plus epsilon approximation. And here's your algorithm. So I should say, I think all the algorithms I'm presenting can fit on Post-its. So this is another reason why it's kind of fun to teach. And there's also another sense in which a lot of data stream algorithms are very space-efficient algorithms. So this is an algorithm. This is a version, or this is a result by Seppier in Source 24. It's going to use R passes. And in each pass, what you're going to do is you're going to sample n over epsilon edges. Like if you go through your stream, sample those n over epsilon passes. At the end of the pass, you're going to compute a maximum matching amongst the sampled edges and a minimum vertex cover amongst the sampled edges. And you're going to you can maintain a maximum matching and a minimum vertex cover in order and space. You're actually going to keep track of all the maximum matching, all the minimum vertex covers you're going to use over all the passes. But R is actually going to end up going to just be order log n. So you're going to have space to maintain all the maximum matching and the vertex covers. Okay. And when it gets to the end of the stream, what you're going to do is, of all those maximum matches you've constructed, you're going to return the biggest one. Okay. So why did we bother computing minimum vertex covers? Well, let's go back to what we were doing during the stream. I said we're sampling n over epsilon edges. Now, we're not actually going to sample these n over epsilon edges uniformly. Rather, every edge we encounter, we're going to give a weight to. And the weight of an edge is going to be a function of the vertex covers we've produced. So when we go through an edge in a given pass, E is going to be sampled proportional to some importance factor, which is 2 to the power CE. What is CE? CE is the number of sets amongst U1 up to UP minus 1. So the vertex covers generated in the previous passes that don't cover E. Yes, sorry. There's an important word, don't here. Okay. Okay, so that's the algorithm. Now, I talked about uniform sampling via L0 sampling. Since these explicit weights I can put in, I can either adjust L0 sampling to deal with sampling uniformly, or sampling, or basically treating an edge with multiplicity to the CE as basically 2 to the CE slightly different copies of a single edge, or there's other techniques, things like L1 sampling, that allow me to sample according to weights. Okay, but that's the algorithm. And if nothing else, it looks pretty elegant, looks pretty simple. So why does it work? Well, remember that a random fact I gave you about L0 sampling, which is that if you sample n over epsilon edges, compute the vertex cover of those n over epsilon edges, then I argued that you'd cover at least a 1 minus epsilon fraction of edges in the original graph. Well, from this, you can say that suddenly U1, initially, what are these importance factors? Well, all these important factors are going to be 1 in that first pass. You're going to be uniformly sampling the edges. And so you can argue that the sample set, the vertex cover amongst the sampled set of edges cover most of the edges in the graph. And this actually kind of, the same analysis you used to prove that will apply that, like, kind of, even when I weight the edges, since I'm sampling proportional to those weights, like, you know, the total weight of the total weight of things that I don't cover is also going to be an epsilon fraction of the total weight. Okay, and that's going to give us the following fact: that if this is important for a single edge, the total importance is just this summed over all edges E. And so we can argue, like, with high probability over this random sampling of edges, that the total importance, the sum of all those important terms, grows pretty slowly. It grows by most of factor 1 plus epsilon over 2 factor in each pass. Either you can see this as an extension of the fact that this is true when all edges have uniform weight, or you can just take it for granted at the moment. Okay, so if the total weight grows by a factor 1 plus epsilon over 2 in each pass, and what was the total importance initially? Well, those 2 to the power, in the first pass, all these importances are going to be 1. So initially, the importance is going to be 1. If it increases by a factor of 1 plus epsilon over 2 in each pass, after R passes, this is going to be the total importance. And what's the importance on a single edge? Well, it's going to be 2 to the CE. You can do some algebra here and solve for CE, and you get that CE is less than epsilon over R when R is sufficiently large. Okay. So what does this mean? Remember, CE is the number of vertex covers that don't cover E, because I foolishly left a don't out there. Okay. So if CE is less than epsilon over R, it means that amongst all the R vertex covers, at most epsilon R of them, a tiny fraction of the vertex covers didn't cover E. Okay. So if you pick say a random vertex cover here, like, you know, a random vertex cover out of U1 up to UR, it probably does cover E. Another way to express this is if you take the average of all the vertex covers, and this is a fractional vertex cover. Okay, by average of U1, U up to R, like if you think of these are just integral vertex covers, so you can write them as vectors of kind of 1s and 0s. So here I'm just like kind of summing up the vectors and dividing by R. That's my fractional vertex cover. And now I can complete the argument pretty easily, at least in the case of bipartite graphs. Because if the graph is bipartite, then the best of those matchings I can construct is going to be better than the average of the matchings. And then one useful fact about bipartite graphs is the size of a maximum matching in a bipartite graph is exactly the same size as the minimum vertex cover of a bipartite graph. So M1 has the same size as U1, M2 has the same size as U2, et cetera, et cetera. So we get this equality here because of its bipartite graph. And then by the fact that the average of U1 up to UR was a fractional vertex cover, I can argue by LP duality that the average of the vertex covers is going to be bigger than the size of the best fractional matching, but certainly the best integral matching by 1 plus epsilon. So you get the best matching you return in the last pass is at least the best matching you discover is bigger than the ultimate matching modulo a factor 1 plus epsilon. Okay. Any questions?
Sorry.
Yeah.
That's going to be a very dumb question. So in the argument right now, it looks like there's a bound saying if I take R large enough, something happens.
Yes. Where did that manifest? Or
yeah, like, is there any other constraint on R? It just seems like if I just put, is it to get the average after that?
No, the only place where R comes in is like, if you sat down with a napkin and solved this thing, you'd have an extra plus log, like you could write this as 2 to the power something, you'd end up with a plus log m. You want this R to dominate that m term. That's the only place that you need that fact.
You take the average over R things after that.
Yes. Yeah. But after that point, all you need to get to that point, that's the only place where the random argument comes in. Okay. So we can get a factor, we can beat a factor 2. In fact, we can get a factor 1 plus epsilon if we have multiple passes. Is there anything we can do? Is there anything we can do in the insert delete setting, at least in one pass? Ideally, I would prep Sepia to shout out no at this point. So, Sepia and Gang say no constant approximation allowed for you in one pass in the insert delete model. And in fact, we now know for non-constant approximation, we now have a kind of we know exactly the trade-off between the amount of space you need and your approximation factor. Okay, this is a bit depressing. Is there anything you can do for insert delete for one pass? Let's not deal with arbitrary graphs, but let's say I promise you some things about the graph. We'll look at some special cases. Is there any special cases where something is possible in the insert delete model? Glad you asked. Let's do some more sampling. So far we've seen two different types of sampling. We've seen uniform edge sampling, and then we've had a situation where you could come up with weights for the edges on the fly, and you could sample proportionally to those weights, and pick edge sampling. And given a graph, it proceeds as follows. So it samples each node with probability 1 over k, and deletes the rest. So let's say the sampled edges are those sampled nodes are those 4 nodes. I then look at the induced subgraph on those sampled nodes, and I sample an edge uniformly from that induced subgraph. Say that one. Okay. So I sample nodes, and I pick an edge from what remains. So it's Snape sampling. Okay. So it doesn't. If you think for a while, this is the distribution you get over edges will not be uniform. Okay. It doesn't take long to commit yourself with that. And what's more is that if your graph has a maximum matching of the size at most k, it's possible to argue that if you draw k squared log k samples according to this distribution, amongst the edges you collect, you will have a maximum of size k. So you actually solve the problem exactly with this number of Snape samples. So how you'd implement Snape samples, I won't go into, but it's basically you could use a hash function to kind of to sample the nodes. This would define the set of edges in a subgraph, and you could use L0 sampling amongst those set of edges. So I said I wouldn't describe it, then I basically just described it. There's not much more to it than that. Let me briefly say why this theorem holds true, at least at a high level. So I said the maximum matching was the size of most k, so let's fix a particular matching of size k. Say it's these 7 edges here. We're going to assume this is maximum, and we're going to focus on a specific edge in this matching, say UV. Now, I guess because it's a maximum matching, every edge is going to be incident to one of these kind of yellow nodes. There could be other nodes around here, and maybe you can actually see them on the screen. I'm not sure. But every edge in the graph is going to be incident to one of these kind of yellow endpoints. So let's focus our attention on, let's zoom in on the edge UV. And note that when we sample nodes with probability 1 over k, the endpoints, u and v, were sampled with probability 1 over k squared. And amongst the other 2k minus 2 endpoints, with constant probability, we didn't sample any of them. So there's a 1 over kind of k squared-ish probability that that we sample the endpoints u and v and nothing else. Okay. And what does this mean in the induced subgraph amongst the subsampled nodes? Well, I pointed out that every edge in this graph is going to be incident to at least one of these endpoints here. So in the induced graph, I'm going to end up with this edge, certainly, but maybe some other edges kind of hanging off V or hanging off U. Okay. If indeed amongst those endpoints of the matching, I've sampled U and V and no other endpoints. All the edges are going to be hanging off U, hanging off V, or this edge UV. So if the edge we return by UV samples, by Snape sampling is UV, we're happy. We've collected an edge from the maximum matching. But we're also happy if we've sampled one of these edges, because we might have started looking at this specific matching of size 7, but hey, those three edges and this edge, that's another matching of size 7, so we're fine. Again, there's little details we need to be careful about, but that is like morally why the result is true. So this means for each Snape sample, we will find this edge or an edge hanging off U of V. So if we repeat this process k squared times, or k squared log k times, we will find a good edge for UV. But by union bound, we'll actually kind of like, the algorithm didn't know what U and V we'd zoomed in on. So with high probability by the union bound, we'll find actually an edge. We'll find a set of edges that include either these 7 edges or edges which are just as good as those 7 edges. Okay. So if insert deletes, like if the matching is small, we're fine. The other case where we can do something interesting is for low arbitrary graphs. So a graph has arbitrary alpha if any induced subgraph on R nodes has at most kind of alpha R edges. So for example, people are familiar with planar graphs. So a planar graph has arbitrary 3. Okay. One nice thing about planar graphs, about low arbitrary graphs we could show, is there's a way to assign weights to the edges of a graph, where these weights are just a function, the weight assigned to edge UV is just a function of the degree of U and the degree of V. So I use this formula on the above graph, I get into those weights. So if this graph is low arbitrary, it's possible to show that the sum of all these weights is at most the size of the maximum matching in the graph, and it's at least the size of the maximum matching in the graph divided by 2 plus alpha. So this graph was planar, alpha is 3. So the sum of these weights is a 5 approximation to the size of the maximum matching in the planar graph. So briefly, you can use this sort of idea to get an n to the 4.4/5 approximation, a 2 plus alpha approximation to the size of the maximum matching in a low arbitrary graph using space roughly n to the 4/5. Okay. The basic idea is if the matching is small, you just use that algorithm I just showed you via Snape sampling. And if the matching is large, the following approach works. You just kind of, you sample a bunch of nodes in the graph, and you store all the internal edges amongst those edges. Sorry, you sample a bunch of n to the 4/5 nodes in the graph. You collect all the edges internal to those nodes. You also compute all the degrees of those nodes. So you end up working out the weights of a certain subset of the edges of the graph. And again, you can just apply sort of Chebyshev, Chernoff style analysis to argue that if the quantity you're trying to estimate was sufficiently large, then you can get your 1 plus epsilon approximation to the sum of the weights, and therefore a 2 alpha plus epsilon approximation to the size of the maximum matching. Okay, that's all I want to say about matching, unless there's any questions. Okay, let's do something a little bit different. Let's look at connectivity, where the techniques are really quite different. So if matching's got you down, feel free to come back. So what could we do 20 years ago? We could, in one pass, if there were only insertions, we could work out whether the graph was connected. How could we do that? We could do it in a fairly simple way. Like we basically kind of, we build up a spanning forest. So we store the first edge, we store the second edge. If the third edge completes a cycle, we ignore it. Otherwise, we store the edge. And every edge that comes along, if it doesn't complete a cycle, we store that edge. Okay. If you can actually do slightly more than this. If the set of edges you're maintaining is H, and rather than asking does this edge complete a cycle? You ask, does it complete a short cycle? If it does, you ignore the edge. If it doesn't, you store the edge. Then you actually kind of approximate distances up to a factor order t with slightly above semi-streaming space. Okay, that was 20 years ago. What has been achieved in the last 20 years? Well, it turns out a lot. Like, rather than just working out whether the graph is connected, we can work out how connected it is in the sense of, is it the case that every cut has at least kind of k edges across it? Is it the case that there are k nodes whose removal would disconnect the graph? Can we approximate every cut in the graph? Can we construct cut sparsifers and fetch sparsifers? We can now do, at least initially, all this stuff was developed for just streams that just had inserts and no deletes. Okay? And the general consensus for at least 8 years until 2012 was that even to solve the basic problem of connectivity in one pass, when there's inserts and deletes, was going to require omega n squared space. Okay. Because suddenly, clearly, like any algorithm which is like store the edge unless it completes the cycle is going to be doomed because some of those edges that you previously stored could be subsequently deleted. Okay. So everyone believed this. I certainly believed it. I think most people believed it. That there's really going to be no non-trivial algorithms for connectivity when there were inserts and deletes. And I and everyone else turned out to be wrong. So to describe the next result, I'm going to switch gears a little bit. Rather than thinking about streams, I'm going to think about a kind of a communication sort of like kind of game. And I'm going to kind of like map this back to streams in a second. Okay. So the game is as follows. So imagine you have n people in a social network. Okay. In this social network, kind of various people are friends with various other people. And so they each have a list of their friends amongst the social network. Equivalently, there's an adjacency matrix of a graph. There's n players. Everybody knows one row of the adjacency matrix. Okay. And the communication game we're going to play is that everyone interested has that data, that local information to themselves. And they simultaneously need to send the message to some authority figure, or some central player, such that the central player can work out whether the underlying social network is connected. Okay. Obviously, they could all send order n bits, and the central player would kind of end up receiving all those messages and be able to reconstruct the entire graph. We don't want to reconstruct the entire graph. We just want to know the Boolean question, is the graph connected? Turns out that polylog n bits from each player suffices. Actually, this polylog is exactly order log cubed n bits suffice. And I think this is a little bit surprising for the following reason. Like, let's suppose the graph was such that on the left-hand side, you have this kind of dense component of like roughly n over 2 players, or n over 2 nodes. On the right, you have roughly n over 2 nodes there. And then there's 2 players, we'll call them Cameron and Eduardo, where there's a single edge between these 2 players. Okay. If this edge, well, there may or may not be a single edge. If that edge is present, because this was densely connected and this was densely connected, if this edge is present, the graph is connected. And if it's not present, the graph is not connected. Okay. So this central player needs to know about the presence or absence of this edge. If you think about it, like Cameron has this like a very local view of the world. He's friends with a whole bunch of people over here, and there's a single edge going out here, but he has no notion of over here versus over there. So this friendship is just as special to him as any of these other friendships. So if he's going to send some information to the central player that indicates whether this edge exists or not, he essentially needs to send, or it seems he needs to send information about all these incident edges. Well, that feels like pretty convincing, right? And this is part of the reason everyone thought like kind of connectivity things were doomed if you worked via sketches. It is true that kind of Cameron doesn't need to indicate this edge. Like if Cameron doesn't indicate whether this edge exists, then Eduardo needs to. Okay. So I think, so this is the reason why I claim this theorem feels a little surprising, both at the time and still a little bit in retrospect. Okay, so let me show you how the theorem is proved. Well, at the high level, because this high level is going to kind of apply to a bunch of results. The idea is that each player is going to encode their local information as a vector, and then it's going to send a random projection of that vector to the central player. Okay? We're not going to just send any old sketch. The sketch is going to be designed in a kind of careful way. And basically what I need to spend most of the next 10 minutes talking about is like, how do you design a sketch that's useful for this process? And then what's going to happen is, well, like I could have sent all my original data, all this original graph data, all the rows of the adjacency matrix, and I could run a kind of a conventional algorithm on all this original data and get my answer, is the graph connected or not? What I'm hoping my sketches enable is that if I sketch each of these address books or each of these rows of the adjacency matrix, that I end up with sketches of these rows. So there's a lot less data here. This has been compressed a lot. I'm hoping I can run the original algorithm or something equivalent to the original algorithm on the compressed data and end up with the same answer. That's the hope. Okay. Big mystery about like, well, what's the algorithm I'm trying to emulate in Sketchbase, and what is the sketch M? We'll get to that. Okay, so let's get to it now. So I need to tell you two things. I need to tell you what's the basic algorithm we're going to emulate in Sketchbase, and what sketches will enable to run that basic algorithm. Okay. So the basic algorithm is basically Brooks's algorithm. So as a reminder, for every node in the graph, you're going to pick an incident edge. So if this was if this was the massive graph in question, for each of these nodes, I'm going to pick one incident edge. We'll call that red. I guess for this, so this node must have picked this this incident edge, and this guy must have picked this red incident edge, and this person must have picked that one, and that person must have picked that one, but we don't know whether this one picked this one or this one. I know. Every node picks one incident edge. I've called those red. I can then look at the connected components of that graph, and so there's amongst the red edges, I've got connected components of size 3 on the left, connected component of size 2 on the right. And then for each connected component, I pick a random incident edge. In this case, the graph is sufficiently small that like each of these connected components, there's actually only one outgoing edge. So if I pick that, I've got one big connected component, and the selected edges that I've picked across all the rounds kind of connect the entire graph. So this is a pretty simple algorithm. There was nothing streaming about this. This was just a simple process that would left to run enough times. In fact, left to run around log n times would find a set of edges that contain a spanning forest. Okay. So how do we emulate that algorithm based on sketches? Well, what are the sketches? So each node, or the player corresponding to each node, first of all, encodes their local information as a big long vector in the following way. So let's zoom into player 1. So each of these players is going to, player I is going to generate a vector AI. So player 1 is going to generate a vector A1. This vector is going to be have 0, 1, and -1 entries. Okay. It's an n-choose 2 length vector, and so the entries are going to be indexed by node pairs. So 5 nodes, so I've got like a 5 choose 2 entries here. And basically, an entry is going to be non-zero if this pair is an edge incident to this node. So player 1 has links to node 2 and node 3. So 1, 2 and 1, 3 are non-zero, and everything else is 0. A2, similar sort of deal. A2 is friends with player 1 and player 3. So the non-zero entries in this vector are going to correspond to the entries 1, 2 and 2, 3. Because there was the incident edges to 2 were 1, 2 and 2, 3. The only little twist is we're going to use a negative one rather than a 1 if you're friends with someone with a lower label than you. Okay. Expressed differently, this is just, I'm just saying, associate with player I the ith row of the signed vertex edge instance matrix, if you're familiar with those terms. Okay, What role does these plus ones and minus ones have? Well, it has a nice property that if I sum up the vector from player 1 and player 2, some cancellation happens. And if I look at the non-zero entries of A1 plus A2, well, I'm left with, like, in the first coordinate, things canceled, but in the second coordinate, nothing canceled. So I'm left with a 1, 3 as a 1, and the other non-zero entry is 2, 3. And if you look, 1, 3 is exactly, 1, 3 and 2, 3 are exactly the edges going out of the connected components that just contains 1 and 2. And this is true in general. Like, so for any subset of nodes, the non-zero entries I get when I sum up the vectors corresponding to those nodes correspond exactly to the edges going out of S to the rest of the graph. Okay, so what? Well, we're going to combine that with our friend L0 sampling. Okay, so every player, once they've encoded their local information, once player I has encoded their local information as a vector AI, is going to send an L0 sketch of AI. Okay. And that's all they're going to do. Okay, so that's the sketch. That's the algorithm we're going to emulate. Like, kind of, why did that sketch and that? Why was it the case that we could emulate that algorithm in sketch space? So the central player gets these L0 sketches of A1, A2, A3, A4, A5. So when Clement sends me kind of player 1, when you send me kind of the L0 sketch of A1, like, kind of, I will find a non-zero entry of his vector. Non-zero entries of his vector will correspond to instant edges, like, kind of, will correspond to kind of links between Clement and his friends. Okay, this is true for everyone in the audience. So when you send me your sketch, I will learn one of your outgoing edges, which is good because that was the first step of emulating Brusca's algorithm. Okay. What about subsequently? So I find one edge outgoing from everyone in the audience, and I've got these connected components. I now need to look at it. I now want edges going out of those connected components. So at some point in time, based on the information I've got so far, I'll know these S players are in the same connected component, and I'll be looking for an edge that's going from S to the rest of the graph. Well, all I'm going to do is I'm going to take the messages that those players amongst S sent me. This is the kind of, these predictions, they're just vectors. I can sum them up. I'm allowed to do that. Okay. So I sum up the messages that the players in the component S sent me. By linearity of sketches, the sum of the projections is just a projection of the sum. Now, the properties of L0 sampling was that, at least when I applied it to vectors, it would allow me to find a non-zero entry of the vector. So with high probability, I will find a random non-zero entry of this vector. It doesn't actually need to be a random one. I'm just happy with any one. So I'll find a non-zero entry of this vector. But we carefully designed those A1, A2, A3 such that the non-zero entries of this sum is exactly edges that go out from S to V minus S. So the non-zero entries of this vector is exactly the indices of edges across the cut. So even though you just sent me the sketches of your local information, I can start adding up these messages and can work out and infer other edges in the graph when I need them. Again, I'm brushing some stuff under the rug. There's a slight issue about kind of fresh randomness, emulating log n rounds of the algorithm, but it's still going to be a one-time thing that each player just kind of sends simultaneously like a bunch of L0 sketches or log n L0 sketches, and using that I can emulate Brusca's algorithm. Any questions? 15 more minutes. Yeah, okay. So this template of designing some sketches and then trying to emulate an algorithm in sketch space is something that we can do for a bunch of connectivity problems. We can generalize this question of testing whether the graph is connected to testing whether it's k-connected, i.e. whether every edge has at least k edges going across it. Again, by taking a basic algorithm, in this case, imagine that one algorithm for k-edge connected is this. Like you take your graph, it's a non-streaming algorithm, take your graph, rip out a spanning forest. Okay? So now you've got a remaining graph. Rip out another spanning forest. Keep going, k times. And then it's not hard to show that if you keep on ripping out, so let's say the spanning forest you rip out are F1, F2 up to Fk, then it's not hard to show that the set of edges contained in those spanning forests are k-edge connected if and only if the graph G is. Okay. Not going to prove it, not hard to prove that. Again, I want to kind of show another kind of application of this, like kind of, you can do surprising thing when it comes to manipulating sketches. So we're still in this kind of communication world where you have your own local information, you can send me a sketch. Now what you're going to do is you're going to send me whatever sketch you used to do connectivity, but you're actually going to send me k independent sketches, like for the connectivity thing. So I'm writing this as the sketch of G, but really the sketch of G is just the sketches I get from each one of you when you sketch your own local information. So this is just the M messages I get, and this is if I do it again with fresh randomness and do it again with fresh randomness. So I do k times simultaneously with fresh randomness. Well, if you think about what we did for connectivity, not only did we answer the question, the Boolean question, is the graph connected or not? If we looked at the edges that we kind of built up over time, we actually found a spanning forest. So based on running the connectivity algorithm, so based on you sending me the information that sketch G, I can find a spanning forest F1 of G. This is fine, but now I now want to kind of find F2, which is the spanning forest of the graph, the original graph, after F1's been ripped out. Okay. How did I do this? Well, if I take the sketch of G that I've just got from your second round of messages, and then I sketch the spanning forest I've learned from the first round and subtract it off, well, linearity of sketches means that I now have the sketch M2 of G with F1 ripped out. Okay. Now, M2 is a sketch that allows me to find the spanning forest of the graph I'm analyzing. So M2 applied to this connectivity sketch of G minus F1 will allow me to find F2, and so on until I found F1 up to Fk. Okay, I'm going to go briefly through the rest of this section so I can get to some final stuff. So you can do similar sorts of things for cut spacification and indeed for spectral spacification. Like kind of cut spacification, certainly cut spacification is all about like kind of, you can basically kind of turn the problem of given a graph, generating a sparse weighted graph such that the cuts in the sparse weighted graph are very close to the size of the cuts in the original graph. This is just vanilla cut spacification. You can actually write an algorithm that does that basically just has two different components, which is like one, start with the graph, subsample the edges with probably a half and a quarter and then an eighth and a 16th, etc. So you find all these different differently more aggressively sparsified graphs. This combined with the k-edge connectivity algorithm that found those k spanning forests is actually enough to do cut spacification. So I won't go through the details. And so because this subsampling process and because those edge connectivity algorithms were all something that could be enabled by sketches, you could do cut spacification. Another example is like k-node connectivity, where we came up with an algorithm that was k-squared n space, and Sefia and Vinay, Vihan, okay, sorry, can improve last year to kn. And again, it's like it's this nice template of like designing an algorithm for like a non-streaming sort of algorithm for k-node connectivity. The algorithm is of the following form: that given a graph, subsample a bunch of nodes to find an induced subgraph, and find spanning forests of those induced subgraphs, plugging them all together you can argue that that thing is k-node connected if and only if the original graph G is connected. Like, if you're able to write your algorithm in this sort of form, then you can kind of emulate it in Sketchbase. Okay. Last few things I want to talk about, like kind of moving away from connectivity matching and talking about kind of independence and coloring. So these are things that various people have touched on in the last 2 days. So either that's a good thing, that I'm making connections, or it's a bad thing that you fully absorbed everything you heard in the last 48 hours, and this is going to be boring. It's a rhetorical question. I don't need to know the answer to that. Okay. So forget about streaming for a second. What's the simplest possible algorithm you can think of for computing maximal independence set? It's probably like, pick an arbitrary node. Like, add it to your independent set, remove it and all its neighbors, and then repeat. Okay. That is indeed an algorithm that will find a maximal independent set. Okay. Not a streaming algorithm, but it's an algorithm that would work. So you could try and think about emulating that in the streaming algorithm, but if you did, it would require many, many passes, or it certainly seems to. Like, so you basically kind of, let's just think about inside-only streams for a second, although we'll generalize. So you pick an arbitrary node, you can go through the stream, and you can find all its neighbors, and you can kind of mark them as deleted. Okay, so that's one pass. You've now added one thing to your independent set. Now you go to the second pass. So amongst the edges that haven't been marked as deleted, amongst the nodes that haven't been marked as deleted, you pick one. You go through a second pass. You find like kind of all its neighbors. You mark them as deleted. Keep on going. This seems like it could involve many, many passes. And in fact, that basically vanilla idea could involve many passes. So it could involve actually kind of linear passes where n is the number of nodes in the graph. Sometimes I allow multiple pass algorithms. I don't allow them to be linear number of passes. Turns out, however, and this is like related to an idea we saw yesterday in a different context, if you randomize the ordering in which you're picking these nodes when you run this kind of generic algorithm, you can get this algorithm down to log n passes. The basic intuition is that if you pick a random node, you add that to your independent set, and either that node has many kind of has high degree, in which case in one pass you're going to mark many nodes as deleted, so you're going to make progress that way, or else it didn't have many edges incident to it. In which case, why are you only storing edges incident to that first kind of node or that first pivot? Like maybe you could afford to kind of like take your first, second, third, fourth choice and collect all the edges incident to those, and run this greedy process amongst those edges. Okay, that intuition is kind of will lead you to an algorithm that gets you kind of log n passes. A little bit more detail. Let me take that idea and just to kind of end up with to manifest an algorithm that uses not semi-streaming space, but like n to the 1.5 space, but uses 2 passes. Okay. So we first of all like kind of in memory we pick a random indexing of the nodes, so a random ordering of the nodes v1 to vn, and I'm going to let u be the subset of nodes that corresponds to the first root n nodes in this ordering. And then my 2-pass algorithm is going to be simple. It's kind of in the first pass, I'm going to store all edges with at least one endpoint in u. Then I'm going to emulate this greedy algorithm amongst those stored edges. And then the second pass, I'm going to basically kind of hoover up all the remaining edges. So all the edges that have both endpoints unmarked. And then at the end of that second pass, I'm going to kind of like keep on running that greedy algorithm and like run it to completion. Okay. So the only thing really here to analyze is really how much space is this used. Well, in the first pass, I stored all edges with at least one endpoint in U. Well, how many edges were there in U? There's root n. What were the degrees of those nodes? Well, they could be at most, could be at most n. So the number of edges I'm going to have to store in that first pass is going to be the size of u times at most n. Maybe slightly less than n, but that's an upper bound size of u times n. So this u was carefully chosen to be root n. So in the first pass, we're going to store n to the 1.5 edges. In the first pass. And in the second pass, you can argue, yes, maybe I'm running a little short in time, that the number of edges that remain that have both edges unmarked is going to be small. It's going to be sufficiently small that you can hoover up all the edges in the second pass. There's only going to be, well, when you do, you can do so with n to the 1.5 space, because there's sufficiently few edges left. Okay, maximum independence set. A slightly different problem here. Correlation clustering is something else there's been a lot of activity on in the last 2-3 years. So this is the complete version of correlation clustering, where you imagine you have a graph of n nodes, and it's a clique, so there's like all n choose 2 edges present, and every node is colored, every edge is colored red or blue. So for example, this is a clique on 5 nodes where every edge is colored red and blue. And the goal is to kind of cluster these nodes into 2 clusters or 3 clusters or 10 clusters. That's not a parameter. You can cluster them however you like, or partition them in however you like, such that you want to minimize the number of red edges cut and blue edges uncut. Okay. So if I cluster these 3 on the left here and those 2 on the right there, then how many red edges did I cut? Well, just this red edge. How many blue edges were uncut? Well, there's no blue edges internal to this thing. There's 1 blue edge internal here. So I'll cut 1 blue edge and I'll not cut 1 red edge. So I've got this quantity will be 2. For this graph, that's actually optimum. Another way of thinking about it is that if a graph is close to being, if this quantity can be made very small, then the adjacency matrix of the red edges is almost a block diagonal matrix. Like if you look at those red edges, it forms a bunch of kind of disjoint cliques. So there's various ways to solve this in a non-streaming setting. One particularly appealing, it's not the best approximation, but one particularly appealing algorithm that yields a 3 approximation is take your graph, pick a random node. Okay, form a cluster with that node and all of its incident edges where the edge to that incident, pick a random node and form a cluster with that node and all the nodes that are joined to that initial node by a red edge. So if indeed the graph was a perfect set of like red cliques, you pick a node as one of those cliques, and then when you find all the neighbors that are joined by a red edge, that's going to be one of the cliques in the input. Okay. So remove cluster and repeat, and this yields a 3 approximation. Well, this is essentially the same as the independent set algorithm we just saw on the last slide. And so it can be implemented in log n passes. And so one thing that's happened over the last, I guess, 4 or 5 years is that people have come up with kind of better and better, more and more passive efficient algorithms for doing correlation clustering. And so the state of the art is a 3 plus epsilon approximation in 1 pass semi-streaming. Uses polynomial time. So normally I don't care about the rank time of these algorithms. Like normally one of the things that's typically happened in the context of streaming is people just care about minimizing the space. It's not that time isn't important, it's just like kind of focus on one thing and do it well. And then sometimes other things sort themselves out after the fact. This is one of those strange problems where it's actually quite easy to come up with a 1 plus epsilon approximation in 1 pass using the semi-streaming space, but you're going to need exponential post-processing time. And that's basically kind of connected to this remark I made about adjacency matrices. That you can, there's various streaming techniques out there that allow you to estimate the L2 difference between input data and some kind of other matrix. Okay, so there's an incredibly ugly algorithm that basically kind of sketches the adjacency matrix for your input and basically kind of like takes exponential time to compare that to all possible kind of clusterings of the graph and returns the best one. It's space optimal, but it's not an algorithm you'd ever want to use in practice, and it's super ugly. Okay, fortunately, I was going to talk about SEPI is like a really nice kind of palette specification algorithm, but he talked about it yesterday. And so fortunately, because I'm 1 minute over time, that was his really nice algorithm. There's some analysis, which is the space analysis of this algorithm, where it's pretty kind of easy to analyze. The fact this is correct is a super technical proof, but SEPI has promised everyone interested that he'll go through it in full detail over the break and lunch, and if you're staying for the next few months, he'll keep going through it. But he's already shown you kind of a weaker result, which like captures why something interesting could happen, but really doesn't capture the magic of the fact that his algorithm achieves this delta +1 coloring. Okay, so wrap up. Many other graph problems out there, many of which I haven't had a chance to talk about. Maybe they didn't fit on a single post-it size description. Maybe I didn't already have slides on them. A lot of stuff, like general catches of things I didn't talk about. I didn't talk about anything about kind of graph verification algorithms. I didn't talk about directed graphs. I didn't talk about kind of robust algorithms, like kind of for graph problems. I kind of, a lot of this stuff is close. Like I focused on graph algorithms, so every edge has 2 nodes, like graphs do. But you can ask many of these questions in the context of hypergraphs, or more generally, that you could think about the input sequence as a collection of sets. You can ask kind of like other combinatorial optimization problems, like kind of set cover, hidden set, max key cover. So that was the summary of what we had. I hope I gave you a rough feel for what's out there. I hope I conveyed why I think it's kind of like, I love these algorithms are kind of surprising, they're kind of like neat. They kind of use left field ideas, and there's many fun uses of randomness. And if there's, happy to take questions or chat about it.
Questions?
Has there been a lot of progress in estimating the sizes of optimal solutions?
There is some work for the case of matchings, like kind of like a lot of the work. Well, except for the stuff about well, yes. There are some slightly different kind of upper and lower bounds for estimating the size of matchings in the dynamic model versus actually kind of finding edges of a large matching. Already in the case of like kind of low avericity graphs, like even if a graph is low avericity, you could still have a matching of size n, and we were coming up with algorithms that used n to the 0.8 space, which was just going to be estimating the size rather than the matching.
Small space regime, like polylogs or something.
In polylogs, there's a nice paper by Michael Kakalov 10 years or so ago now, which is like if the graph is in random order, that he found maybe a polylog factor approximation to the size of the matching. And yeah, so there's stuff out there, yeah.
Cool. Any other questions?
Do you have a favorite problem in search and deletion streams at this point? Like, what is the open problem there?
Aside from the ones that you've solved during you told me that you've solved in the last couple of days.
Single pass.
Single pass. I think it's got to be spanners, like kind of. So I mentioned that kind of like about 20 years ago, we had that simple algorithm for estimating all distances up to a factor 2t minus 1, and the algorithm used to kind of n to the 1 plus 1 over t space. That was all fine if you were just doing insert delete. We still don't know unless SEPI is hiding something, we still don't know anything about kind of whether you can do semi-streaming in one pass with insert and delete to construct spanners. We know certain classes of algorithms can't achieve it. We know multi-pass algorithms that can achieve interesting trade-offs, but I'd say that thing for one pass would be a good example.
So you mentioned time, like this exponential time for the 1 plus epsilon approximation. So is that open, or is that, do you know? I mean, is it NP hard or?
So for correlation clustering, It is APX. The non-streaming problem is APX hard, so I can't. So I think there's some constant you can't beat.
Right.
Whether in streaming you could get a one-pass algorithm that would get the constant approximation down to something like you can get in the non-streaming setting with small space and fast is open, I think.
And other problems with interesting open timing problems?
There was some another example of this kind of like moronic algorithm that just sketches something and then goes through an exponential number of things to check. I think there was a paper I had with Amit, who's, you remember this paper, don't you, Amit? It's great. And he was like, he was checking his laptop, so I knew I could ask that question. Which was the problem in our directed graph stream problem where you just like, did the moronic thing, but you got to the end of the stream and then you just checked an exponential possible number of options. Was that feedback arc set for complete graphs for tournaments?
Yeah.
So feedback arc sets for tournaments, I think was another thing. Although there has been some subsequent work on that, and I can't remember what that subsequent work achieved.
Thank you.
Cool. All right. So I don't want to keep people from their morning coffee. So let's thank Andrew again. And we'll reconvene at 11.